Hi, I'm Miss Hearn. Let's get started. In this video, we're going to talk about how to simplify, add, and subtract radicals. In order to do that, there is a basic idea of radicals that we need to understand. We've talked before about how we can take, for example, the fourth root of a number, noting the index. We call this little number in the crux of the radical the index, is a fourth root. Then we know that we're being asked the question, what number raised to the fourth power is actually equal to 16? And one way to solve that problem is to just think about powers of 4. 1 to the fourth is 1, 2 to the fourth is 16. So what number raised to the fourth power gives us 16? Well, that would be the number 2. But another way of thinking of this is that instead of having a 16 written under the radical, we could think of this as a 2 to the fourth power written under the radical. And so you can actually think of the radical and the power having the same index as exponent. It cancels out and we're left with just 2. Let's think of it that way for the next exercise. Cubed root of 343. Well, 343 is exactly 7 to the third power. So this is the same as the cubed root of 7 to the third. And you can think of it as the cubed root undoes the third power. As long as the index and the power are the same, they reverse each other, and so we're left with a 7. That helps us when we're in a situation like this last box on the left, where we have the fifth root of x to the fifth, and all we know is that x is some positive number. So I can't look it up on my list, but what I can do is I can say, oh, the fifth root of a fifth power, they're going to cancel each other out, and we're going to be left with x. So in general, if you have the nth root of some number to the nth power, as long as the base x is a positive real number, then you know that the result is going to be the number x. And it doesn't matter what is going on inside, what x looks like, those n's will cancel out. So let's take a look at this example. We're asked to simplify the radicals. Assume that variables represent positive real numbers. In part A, we have x squared under the radical. It's a square root because the index is not written. We assume that it's a 2. So the square root of x squared, since x is assumed to be a positive real number, things get a little tricky when it's not. As long as it's a positive real number, the square root undoes the squaring, so we're just left with an x. Similarly for part B, the cubed root of a cubed, we're just left, since the index matches with the power, with just an a. Now let's look at C very carefully though. For C, we have the square root of x to the fourth. So you might think, oh no, we're stuck. But in fact, it turns out x to the fourth is actually a perfect square. Let me show you why. I'm going to claim that x to the fourth is the same as x squared squared. So what does that mean? That means when we square something, we're multiplying it times itself. X squared times x squared. How many x's do we have altogether? That's x times x times x times x, which is x to the fourth. You may have learned that when you raise a power to a power, you multiply the exponents, or that when you when you multiply like bases, you add the exponents here. Either way you think about it, you're going to get x to the fourth. So it's true that x to the fourth is a perfect square. It's x squared squared. So in fact, thinking of it as x squared squared, the index is going to cancel out that outer square, and we're going to be left with just x squared. A shortcut way to think of it is as if we divided the power divided by the index. Let's see if it works out for the cubed root of z to the sixth. So again, I'm going to claim that z to the sixth is a perfect cube. What would you have to cube to get z to the sixth? Z to the what cubed would equal z to the sixth. Well, if you raise a power to a power, you multiply the exponent. So we would need a 2 there so that when you raise z squared to the third power, that ends up giving you z to the sixth. So this is a perfect cube because 6 is divisible by 3. That's important. That's why z to the sixth is a perfect cube. Okay, so thinking of it as the cubed root of z squared cubed, then the index cancels with this power and we're just left with z squared. Or another way of thinking of a little shortcut is from the beginning, we divide the power by the index. Okay. All right, so this is all well and good when the powers are divisible by the index, but sometimes that's not the case and we'll still be asked to simplify radicals. In order to do this, we're going to need to use this fact that the nth root of a times b is equal to the nth root of a times the nth root of b. I like to think of it as you can break apart radical expressions if you have multiplication inside the radicand under the radical. As an example, if you had the square root of 25 times 4, we could break it apart into the square root of 25 times the square root of 4. And this is true because 25 times 4 is 100, square root of 100 is 10. And on the right side, we have the square root of 25 is 5, and the square root of 4 is 2. 5 times 2 is also 10, so it works out. Okay, so we're going to use this fact to help us simplify radical expressions. By the way, there's a corresponding rule over here on the right that has to do with when you have division under a square root, in other words, fractions, but we're going to work on that later. Right now we're going to focus on simplifying square roots that don't have fractions. And if there's no fraction involved, there is one condition that has to be met in order for a square root to be, or really any radical, but we're going to look at square roots first. In order for a square root to be considered simplified, it has to be the case that none of the factors of the radicand are perfect squares. So square root of 8 does not meet this criteria because the radicand, when I say radicand, I'm referring to the number under the radical. And the number 8 has factors of, remember factors are just numbers that divide evenly into it. 1 goes in evenly, 2 goes in evenly, 4 goes in evenly, and 8 does. Are any of these perfect squares? Yes, 4 is a perfect square. So that means that this is not in simplified form, because it has a factor that is a perfect square. Okay, so one way to fix this problem, if you consider it a problem, which we do in math, is to break this square root apart by thinking of 8 as a product of its factors. Okay, I'm going to actually do this in 2 ways. The first way is rather simple, and you're going to say, Ms. Hearn, we should do this all the time, but unfortunately it doesn't work well with variables. So we're going to also look at another approach, and I'm going to use that one all the time so that you're good to go whenever we have variables. All right, so what you do is you list out all the factors like we've done here, and you pick out the largest perfect square that's a factor, in this case 4. And you're going to rewrite the 8 as a product of 4 times whatever you need. Well, what times 4 is 8 times 2. So we're going to rewrite this not as square root of 8, but square root of 4 times 2. And then we're going to use this idea that we can break it apart into 2 separate square roots. So this is the same as the square root of 4 times the square root of 2. All right? Now remember, 4 is the same as 2 squared. That's what makes it a perfect square. And the square root and the square cancel out. Or in other words, square root of 4 is 2. And we still have that square root of 2 being multiplied by the 2. So this is considered the simplified form of the square root of 8. This is the form that is standard, the one that we would normally use. And it might seem strange, but the square root of 8, if you put square root of 8 into your calculator, you're going to get the same value as if you put 2 times the square root of 2 into your calculator. They're the same number. All right, now I promised we would do 2 methods. Here's the other method. And the one that I'm going to do the most because it applies in the most situations. Instead of looking through a list for the biggest perfect square that goes into 8, we're going to use what are called prime factors of 8. We're going to write 8 as a product of just prime numbers. Primes, by the way, are numbers that are only divisible by themselves in 1, like the number 2, 3, 5, 7, 11, and so on. These are numbers that cannot be divided by anything except themselves and the number 1. So what you do is you take the number you're interested in finding the root of and you break it down into its prime factorization, meaning you divide it repeatedly by prime numbers until you can't do so anymore. I like to start with the number 2 if I have an even number. 2 goes into 8 4 times. 2 is a prime, that's why I'm dividing by it. And I'm going to do it again because 4 also is divisible by 2. 2 goes into 4 twice. And when you see that you get a result that is a prime, you stop, because what that means is you have figured something out. You have figured out that 8 is the same as 2 times 2 times 2. Check it. 2 times 2 is 4 times 2 is 8. In other words, the prime factorization of 8 is 2 to the 3rd power. So the alternate method for evaluating the square root of 8 is to use this form of the number 8, 2 to the 3rd power. Now, we have a square root. The index isn't written, but it would be a 2, right? It's a square root. And we have a power of 3. We would like to have a power of 2 because square roots and square powers cancel each other out. So what we're going to do is we're going to say, well, isn't that the same as 2 squared times 2? I'm going to break apart one of the 2's. And then I'm going to now use the breaking apart the radical. So in one radical, I have my perfect squares. And then I like to say that inside of the other radical, I have my things that are not perfect squares, which I call the leftovers. So you have your perfect squares and your leftovers. One of them is going to simplify. Square root of 2 squared, right? Square root squared cancels out and you get 2. And in the leftovers, we have square root of 2. Notice this is the same result we got a minute ago. Now you might say, but the other way was easier, but I promise you this way is going to help us as we move along in this process. Okay, so the next square root that we're going to simplify is the square root of 160, but we're going to use the prime factorization approach to do it. And then we're going to break it apart into our perfect squares square root and our leftovers square root. But before we can do that, we need to take the number under the radical, the radicand, which is 160, and we're going to break it apart into primes. I've listed some primes so that we can check them off as we go, and make sure we know when we divide and our result is a prime, we know to stop. So I like when I have an even number to start with a 2. You don't have to, but I like to go in numerical order. 2 goes into 160 80 times. 2 also goes into 180, so I'll divide it again. It goes in 40 times. 2 also goes into 40. It goes in 20 times. 2 goes into 20 10 times. 2 goes into 10 5 times. And now I'm going to stop. Not only is 5 no longer divisible by 2, but in fact it was one of the primes on our list. So I know that I have the prime factorization. 160 is actually equal to 2 times 2 times 2 times 2 times 2 times 5. 5 2's and then a 5. But I don't like writing it like that. That's long and cumbersome. So I'm going to write it as 160 equals 2 to the 5th power times 5. So now I'm going to come over and I'm going to work my problem. Thinking of 160 as this 2 to the 5th times 5, I have to take the square root of 2 to the 5th times 5. Okay, but I want to break this apart so that I have perfect squares and leftovers. Well, any factor that has a power higher than the index, 2, you want to look at it and see if the index divides evenly into it. If it does, then it's a perfect square. This one does not. 2 is not a factor of 5. In other words, 5 is not even. But what could I do about that? Well, I could think of that 5th power as 2 to the 4th with 1 2 left over. 2 to the 4th times 2 to the 1st would be 2 to the 5th. So you're breaking off that extra 1 to get an even power so that the 2 goes evenly into it. If it's an even power, that means it's a perfect square. So now I'm going to break apart my radical into the things that are perfect squares and the things that are my leftovers. So the perfect squares are things with even powers, like 2 to the 4th. And everything else, the 2 to the 1st, which I'm just going to write as a 2, and the 5 are leftovers. All right, now, do you remember how we take the square root of 2 to the 4th? Remember how up here we had the square root of x to the 4th? And we ended up just dividing the 4 by 2 and getting x squared. Well, it's the same idea here. The square root of 2 to the 4th is 2. 4 divided by 2 is 2 squared. And then we have the square root of 2 times 5 is 10. So we're going to have 2 squared, which is 4, times the square root of 10. And you could confirm this on your calculator. If you took the square root of 160, it's actually the same as 4 times the square root of 10. But 4 root 10 is considered the simplified form. Why? Because notice that 10 has no factors that are perfect squares. Only 1, 2, 5, and 10 go into 10 evenly, and none of them are perfect squares. Okay, let's do one more. This one has a number and a variable in it, but that's okay. It works the same way. The first thing we're going to do is we're going to make a note of our primes. So our primes are 2, 3, 5, 7, 11, 13, and so on. If we have to go higher, we will, but not likely in this problem. And we're going to divide 48. Since it's an even number, I'll start by dividing it by 2, and let's see what happens. 2 goes into 48 24 times, 2 goes into 24 12 times, 2 goes into 12 6 times, 2 goes into 6 3 times, and I stop because 3 is a prime. So that means that 48 is equal to, let's see, we have 1, 2, 3, 4 2s, so 2 to the 4th times that 3 at the bottom there. That's our prime factorization of 48. So inside of our radical, instead of having 48x to the 6th, I'm going to think of it as the square root of 2 to the 4th times 3 times x to the 6th. Okay, now the next thing we need to do is to recognize what are perfect squares and what are leftovers and split it apart into the two different radicals. Notice that 4th power here is a perfect square. An even power indicates a perfect square. It's divisible by 2. So this is going to go into our perfect squares category. The 3 has a power of 1, which is not an even power, so that's going to go in our leftovers. The 6 has an even power as well, so that is a perfect square. So that's going to go into our perfect squares radical. All right, now to simplify, divide the index into the exponent. So the square root of 2 to the 4th is going to be 2 squared, because 4 divided by 2 is 2. And the square root of x to the 6th is x cubed, because 6 divided by 2 is 3. And there's nothing you can do with the square root of 3, it stays the same. So your final answer is going to be 4, because 2 squared is 4, x cubed square root of 3. I hope you found this video helpful. If you did, please remember to give it a thumbs up. That'll help other students to find the video.